I'm going to talk about the binomial distribution. The binomial distribution is a useful way it's a formula, and it's a useful formula for determining the probability of having a certain number of successful outcomes out of a certain number of trials, in which you know the probability of a success or failure for each individual trial, and the probability has to be the same with every single trial, and that's very important. If there are different probabilities for some trials versus other trials, then you can't use this formula. But if you can, then it's useful, and I'll explain why this formula is what it is. We've already talked about permutations and combinations in my other video titled Permutations and Combinations on YouTube. So if you see that video, that would help you understand what I'm going to talk about today. After this, I talk about a little bit more about the binomial distribution and how to approximate it with the normal distribution, and I also talk about the Poisson distribution and how to derive the Poisson distribution from the binomial distribution when we take the number of trials and we raise it to infinity, how you can see the relationship, how the formula becomes what it is. So first, I want to introduce my key here. N is the number of trials. P is the probability of having success on an individual trial. X are the number of successful trials. P of X is the probability of having a certain number of successful trials exactly. If we use greater than or equal to, that's greater than or equal to a certain number of trials, that probability. Or if it's less than or equal to, that would be the probability of having less than or equal to that many. So first I want to kind of review what we talked about before. We talked about having 4 cards, or 6 total, but we're just drawing 4 of them. And we talked about the permutation equation, using that to figure out the number of different ways we could choose 4 cards, that we could take 4 cards out of those 6 cards. And that's when the order of the draw matters. What card we get first, what card we get second. Do we get an ace first time, 2, 3, and 4? Or if we don't care about the order, we would use a combination problem, because we divide out the order, the number of different ways that we could draw these cards. They're all the same probabilities, or they're just as probable, just as likely. So we multiply time, or basically we divide times. We multiply in the denominator. We divide out the number of ways that we can draw those specific cards, and then we can find the probability or the number of combinations. So in the case of the 6 cards, there are 360 ways to draw 4 cards if you're caring about the order of these cards, when it's 4 out of 6. And there are 15 ways to have these 4 cards, but to have 4 cards when you don't care about what the order of those 4 cards are. There's 15 combinations of cards, and that's why it's a combination problem. So when it's a permutation, we're dividing out the number of cards that we didn't draw over here in n minus k, because k is the number we're drawing. So we take n minus k to find the number of cards that are remaining, and we want to find out how many different ways we can order these cards and divide that out, because we don't care about the order of these. We only care about the order of these. In a combination problem, we also don't care about the order of these, so we also divide out k factorial, which would be 4 factorial, 4 times 3 times 2 times 1, and then we get 24. By the way, n factorial means you take and you multiply serially all the way down to 1, starting with the last number, basically. So if there's 6 of them, we go 6 times 5 times 4 times 3 times 2 times 1. And when you do that, you get 720. There are 720 ways to order these cards if you're looking at all 6 of them. Because the first one, you have 6 choices, then you have 5 choices after you've chosen that already, and there were 6 of those. Then you'll have 5, then you'll have 4. You have to multiply all these because they're all independent. Well, at least when you multiply them, you get n factorial. So when we did that, we got 720 divided by 2, because there were only 2 remaining. 2 factorial is 2 times 1. and you divide 720 by 2, you get 360. Then when you divide 360 by 24, you get 15 for the number of combinations. So let's look at permutations and words real quick. So for the word phoenix, there are 7 letters. They're all unique letters. None of them are the same. And so how many different ways can we have these 7 letters? Well, there are 7 factorial ways to do that. And then if we use this formula, the denominator still becomes 1, because we're taking 7 and we're subtracting 7, because we're still drawing all 7 letters. So 7 that we started with and 7 that we're drawing, that gives us 0. 0 factorial is actually 1. And that's one of those strange rules, but if you want to think about it this way, there's one way to draw no items, if you want to think about it that way. So what is that? What's 7 factorial? Well, 7 factorial is 5,040 if you do it on a calculator. So there are 5,040 ways to do this, to sequence those letters. What about when there are duplicate letters? So we could use any of the 4 S's to get the first S that we put in there, wherever it is, when we're randomly doing it. Say we're to draw an S out, well, we could draw from one of 4 of them. And then we could draw from one of 3 of them. Then we could draw from 1 and 2 of them. So we actually want to multiply those together. So that would be 4 factorial. We got to divide out. Plus there are 4 I's. So we also got to multiply that times 4 factorial for all the I's in Mississippi. And then we got to also divide out the 2 P's, the ways we can order those. We could draw 1 P, then we could draw another one. So we actually end up going, this ends up being 0 factorial again, because we're just taking all 11 cards, and we're all 11 letters, and we're seeing how many different ways we can do that. We have 11 factorial up here. Then we're taking that and we're multiplying it times 4 factorial in the denominator. And then we're multiplying it times 4 factorial again for the I's. And then we're multiplying it times 2 factorial for the P's. When we do that, we end up with 11 factorial divided by 4 factorial divided by 4 factorial divided by 2 factorial. Oops. Divided by 2 factorial. And we get 34,650 if you do that on a calculator. What about if we just have 2 kinds of letters in there? We only have P's and A's. The word Papa. And the reason that I'm doing this is because up here we only have 2 kinds of outcomes if we're looking at the sequence of trials, successes or failures. So if we want to think about it kind of like a word in which we have just 2 kinds of letters in it, first, there are 5 of them. There are 5 letters. So we go 5 factorial. Then we want to divide by, we're actually drawing all of them. So we also want to take and do 0 factorial, because 5 minus 5 factorial, that's 0, so that's still going to be 1. Then we want to take that times, where's the blue one? There's the blue one. So we want to take and we want to multiply by 3 factorial, because there are 3 ways, or there are 6 ways to rearrange those 6's, or if you want to think about it as drawing those out, which we kind of basically do when we draw out the successes out of all the trials that we do up there. When we do that, there are 6 ways to do that. Then we also got to take that times the 2 factorial, because there are also 2 ways to draw out the A's. One A or the other, if you want to think about it that way. When we do that, we end up with 10, because we take basically 120 divided by 6, that gives us 20, but then we also got to divide out the 2 ways that we can get the a's. When we do that, we get 10, because we've got to divide by 2. So there are 10 ways to have basically 3 p's organized within the word papa, or if we just took the letters and we rearranged them. There are 10 ways to rearrange them if we don't care about if we don't care about each p having its own identity or each a having its own identity. So let's say we want to know the probability of rolling 3 6s exactly when we're rolling 7 dice. So to get a success, it's a 6. So the probability of rolling exactly 3 6s, if n equals 7 and x equals 3, because that's the number of successes, the probability is 1 in 6 of doing that. This is the formula we get. The probability of x equals n choose x times the probability of getting a 6 raised to the number of successes we're looking for, which is 3, times 1 minus the probability of getting a 6, because the other ones are not 6s. And we take 1 minus 1 6, that's 5/6 chance. And then we raise it to what's left over, all the failures, the number of failures. That's 7 minus 3, so that's 4. So we would take 5/6 to the 4th, there. When we do this, we get the probability of doing that. Why? The probability of rolling 3 6s is the same no matter which dice are 6s, so long as there were exactly 3 6s after all dice are rolled. It doesn't matter which ones were 6s. We could be the last 3 rolls that we get 3 6s in a row, or the 3 6s may not even be next to each other in the sequence. So those probabilities are all the same. If we could just know what all of them are, then we would know what the probability is of rolling 3 6s, regardless of what the order is. And that's the idea. So we can find all scenarios and add their probabilities or multiply. We can multiply here, that's the key. Since they're all the same, we can just multiply all the ways to do it. So multiply the number of qualifying combinations of rolls by the probability of getting any one of the permutations. So if we just look at this as a permutation, and we also take into account that a success is a success no matter what, no matter which trial we got it from, which order we're seeing a success or a failure. So the first failure, was it towards the end, like on the 4th one, and then the second here, and then the 3rd there, and the 4th there? We don't care what order they're in. So we got to divide that out. We got to divide factorial of that. And we also got to divide factorial of the number of successes, because we don't care about where the first success was. If you think about these dice as being named, like they all have a name, Lenny, Jenny, Kenny, Timmy, Jimmy, Kimmy, or Ned, we don't care about which one of those guys ended up being what number. So that's why we divide it out, kind of like we did down here. So when we do this, it comes out to be just like this formula here, or if you want to think about it as a permutation like we did here, you can think about it either way. You could think about the combinations as, except in this case, we know which ones are successes already. How many different combinations of 3 can you grab? Well, there ends up being 35 if you use the combination formula. 35 different ways to pull out 3 dice. But we want just the first 3 of them in this situation at the beginning when we think about it this way. We want just the first 3 to be that way. If you think about it that way, that's 1 in 35 that we'd have it this way. But we're not trying to find probability, we're trying to find the number of combinations, if you're thinking about it that way. So it's actually going to be 1 over the probability, which should be 35. You get 35, and that's why we can use the combination concept here, because we're actually just looking for the number of them. When we do that, and then we multiply times it being just in one specific sequence, we can also come up with the answer. So when we do this, we end up taking 1 6 times 1 6 times 1 6, that's why it's 1 6 cubed. And then it's 5 6 times 5 6 times 5 6 times 5 6. That's the same thing as 5 6 to the 4th. When we do this and we multiply it by all the ways that we can do that, because we're not just looking for that specific one, but if we know one of them, we can figure out all of them if we know all the different ways to do it. And what we ended up doing here was dividing the number and then dividing it by the ones that weren't successes first, if you think about it that way. Once you've done that, now you can look at you can even think about it this way. There are 7 different ways to pull the first one out of the whole order of whichever ones were successes. Then there are 6 ways to pull this one, and then there are 5 different ways to pull that one. But you don't care about which one you pulled first of those 3. That's why we have to also divide by 3 factorial in the combination problem there. And then when we do that, we get 35. So this is pretty useful for a lot of things if you just want to know the probability of having a certain number of successes, but you have to be able to break it down to success or failure. I hope you enjoyed this. Thank you.